two blocks A and B having the same mass collide elastically with each other. Velocity of A before the collision is 10 meters per second. If block A comes to rest after the collision, then what was the velocity of block B before the collision? See, many things are given in the question. First of all, they gave that the masses are same. So if block A is of mass small m, block B is also of mass small m. Okay. Then they gave the initial velocity of A. It was 10 meters per second. And they said after the elastic collision, block A suddenly comes to rest. So final velocity of block A is actually 0. V1 is given to be 0. And they have asked what is the initial velocity of block B. What is the initial velocity U2 of block B? This is asked in the question. We have to determine the initial velocity of block B before the collision. Okay. Now, how are we supposed to solve these head-on elastic collision problems? Well, the simple approach is always begin with two simple equations. We will take a general case in which masses are different, and then we will move to a particular case in which masses are same. Actually, in our question, the masses were same. So we will move into that case. But before that, let's talk about a general case. And in general case, we always begin with two equations. The first equation is from the conservation of linear momentum. Why the linear momentum is conserved? Because in these collision, only the internal forces are involved and there is no net external force on this system. We can conserve the linear momentum. Okay. So, initial momentum P initial is equals to final momentum P final. What is the initial momentum in our case? We have m1 u1 plus m2 u2. This is the initial momentum. And what is the final momentum? Final momentum we can see is m1 v1 plus m2 v2. Okay, this is after the collision. And we can see that u1 was initially greater than u2. This is why m1 approached m2. Okay. Now, the second equation. For elastic collision, energy is also conserved. For elastic collision, momentum is conserved and energy is conserved. So, the second equation we can write it in terms of conservation of energy. But let me give you a simpler way out. The other equation we can also write in this fashion. We can write speed of approach is equals to speed of separation. I will repeat that again. Speed of approach is equals to speed of separation. Did you get that? Okay, I will write the equation. Then you will get it. So, mass m1 is approaching m2. Can you see that? Yes. So, what is the speed of approach? The relative speed. You will say relative speed is u1 minus u2. Yes? Yes. u1 is greater than u2. So, we can see u1 minus u2 is the speed of approach. Okay. Now, after the collision, the two masses separate. Can you tell me the speed of separation? You have to tell me the relative speed. Speed of separation. What is the speed of separation? You will say it is v2 minus v1. Yes, this is the equation. Speed of approach is equals to speed of separation. Okay. Let's call this equation 2. And the earlier equation was equation 1. Now, let's come to the specific case in our question. In our question, they said that m1 is equal to m2. They gave us this condition. And they also gave us the second condition that u1 was equal to 10 and v1 is equal to 0. They also gave us this data in our question. So, we will come to this data, but hold on. Let's discuss this case where masses are equal. What happens when the masses are equal? When the masses are equal, we can convert the equation 1 like this. We can get u1 plus u2 is equals to v1 plus v2. This is from equation 1. How did we get that? Because we have put the masses to be same. Mass cancels out everywhere. Okay. Now let's call this equation 1 dash. This is equation 1 dash. This is for a special case when the masses are equal. Okay. Now if we add equation 2 and 1, what are we getting? We are getting that 2u1 is equals to uh, 2v2. Wow, v2, we got the value of v2. V2 came out to be equal to u1. V2 is equals to u1. Yes, let me write it like this. V2 is equals to u1. And what about v1? V1 is coming out to be equal to u2. Yes, these are the final velocities. And we can see that if we carefully mark, we can see v1 is coming out to be equal to u2. Oh, so the velocities interchange. Did you see that? When the masses are equal, the velocities interchange. Earlier, the first mass, the green mass, was moving with u1. Now the same green mass is moving with u2. This happens when the masses are equal. There is no 1 and there is no 2. When the masses are equal, this happens. Okay, we got it. So, in our case, they gave us the initial velocity of the first mass, the green mass, to be 10. And they gave us the final velocity of the green mass to be 0. V1 is equals to 0. Did you say V1 is equals to 0? Yes. But we know V1 must be equal to U2. Yes. And this means U2 is also equal to 0. The initial velocity U2 of the second mass must be equal to 0. Yes. This was asked in the question. The initial velocity of mass B was asked in the question. So we can say mass B was actually at rest. Wow. So let's first of all mark option B 0 meter per second. Block B should be at 0. U2 should be equal to 0. Now let's see what happens. So we know if the masses are same, the velocities will interchange. Let's see what happens. So block A comes and it hits the block B. Now A comes to rest and B starts moving. A comes to rest because the velocity interchange. Velocity of block B initially was 0. So finally the velocity of block A will become 0. And finally, can you tell me what is the velocity of block B? Finally, the velocity of block B, V2, must be equal to 10. Why? Because the velocities interchange. Okay, the momentum is conserved. The velocities interchange when the masses are same. We got it. So let's mark option B as the correct answer for our question. Let's have a look at this question. In a snooker game, a player strikes the white ball and imparts a velocity of 4 meters per second. So the player hits and the white ball gains 4 meters per second. Awesome. The white ball strikes the another red ball which was initially at rest. Amazing. So this happened. White ball, here it goes, and the white ball hits the red ball and the red ball goes into the hole. We have a nice score. Now, assuming that the collision of the ball is perfectly elastic. So the collision is perfectly elastic. That is, energy is conserved and the momentum is conserved. Okay. And masses of both balls are same. Masses are also given to be same. This mass is small m. This mass is also small m. Okay. Now, what are the velocities of the red and the white ball respectively? So after the collision, what are the final velocities? This is the question. Again, if we repeat the question, before the velocity of white ball was 4 and the red ball was at rest. Its velocity was 0. So these were the initial velocities. And finally, after the collision, we have to tell what are the final velocities V1 and V2. And in the question, they gave that the masses are same. This is a small m. This is also small m. This is small m. This is also small m. Okay, so masses were given to be same and the collision was perfectly elastic collision. Perfectly elastic collision. Now, when we have a perfectly elastic collision, this means energy is conserved and the momentum is conserved. So let's write the equations very quickly. The first equation will be conservation of linear momentum. Initial momentum of the system was m times u1 plus m times u2. Basically, u2 is 0. So, m times u1 was the initial momentum. Okay. And final momentum we can see is m times v1 plus m times v2. Okay, so this means u1 is equals to v1 plus v2 for our case. This is our first equation. Okay, now the second equation. The second equation we can get from the speed of separation and from the speed of approach. We equate them. Actually, we can write the equation of conservation of energy, but that is too lengthy. So we take a simpler equation. The simpler equation is speed of approach is equals to speed of separation. Now, in our case, what is the speed of approach? You will say it is u1 minus u2. Okay, this is the speed of approach. And in our case, it would be equal to 4. Okay. And speed of approach must be equal to speed of separation. So what is the speed of separation? We can see speed of separation is v2 minus v1. Yes, this is equation 2. So 4 must be equal to v2 minus v1. This we get from equation 2, and from equation 1 we got 4 is equals to v1 plus v2. 4 is equals to v1 plus v2. So from these two equations we get these things. Now what we will do, we will add these two equations and we get v2 is equals to 4. This is what we get after we add the equation and divide by 2. Okay, so v2 is equals to 4. And what about v1? Well, v1 comes out to be 0. Oh, this means the velocities get interchanged. Earlier the white ball was moving with 4. Now finally the red ball is moving with 4 meter per second. Okay. And earlier the red ball was at rest. Now the white ball is at rest. So when the masses are same, the velocities get interchanged in elastic collision. Okay. So this was elastic head-on collision where masses were same. Now let's mark option D, 4 meter per second and 0 meter per second. 4 meter per second is the velocity of the red ball and 0 meter per second is the velocity of the white ball. Option D is the right answer for our question. A metallic ball of mass 20 kg. Oh, really heavy ball. Mass M1 is 20 kg. Wow. Now this ball is moving with the velocity of 5 meter per second. So initial velocity u1 is given in the question. u1 is given, m1 is given. Okay. It collides with a small plastic ball of mass 5 gram initially at rest. So here we have a small plastic ping pong ball and its mass is 5 grams. We can write it in kgs. So m2 is equal to 5 into 10 raised to power minus 3. So small, so small. And what was u2? u2 was 0. Initially, this ball was at rest, given in the question. Now, the question says, what is the final velocity of the plastic ball? So, we have to find the final velocity after the collision of this very small ball. So, what is the value of v2? This is the question. Now, at this point, we can see we have a collision of a really heavy mass with a really tiny mass. So, when this collision happens, you can always remember what is the value of v1 and what is the value of v2. You can remember the actual formulas. That would be very useful for you. Now, I am revealing these formulas. As soon as I speak them, try to remember them. Now, they are very simple. First of all, let's talk about v1. What is the final velocity of the heavier mass? Now, this is the easiest one to remember. The heavier mass will suffer a very slight change in its velocity. Its velocity is almost undisturbed. So we can say that v1 equal to u1. Approximately these velocities are equal. So you can say simply there is almost no change in the velocity of the heavier mass. Okay, remembered? Okay, nice. Now let's talk about v2. v2, this velocity will be twice of u1 minus u2. Twice of the velocity of the heavier mass minus velocity of the lighter mass. Now one important alert. These u1 and u2 are with their signs. u1 and u2 are with with signs, S-I-G-N-S. Remember that. People forget that and they make mistake. See, in our case, if we can see 5 meter per second is in positive direction, so we will take the plus sign. Suppose the velocity of the red ball was also in the positive direction, then we would have taken the positive sign for u2. If the velocity of the red ball was in the opposite direction, then we would have taken the negative sign for u2. Okay? Okay. Now these are the velocities v1 and v2. Now can you tell me what is the exact value of v1 for our question? Finally, after the collision, what is the velocity of the heavier mass? Come on, you can tell me now. What is the velocity of heavier mass after this elastic head-on collision? You will say it is equal to u1, which was equal to 5. Yes? Now, what about v2? What is the velocity v2? You will say v2. This is also very simple. It is twice of u1. u1 was 5 minus u2. u2 was given to be 0. So we get 10. Yes. So v2 comes out to be 10. And v2 was asked in the question. So we can mark option A, 10 meter per second, as the right answer for our question. Now you would say, wait for a while. You have told us the formulas, but you haven't given us the reason. We would remember these formulas if you say so, but we should know how these formulas come. Okay? If you want to know, you are very welcome. Now, let me see the situation. Here I give you the initial situation before the collision, and here I give you the final situation after the collision. Do you see these two situations? Yes. Now, I have given the velocities u1 and u2, and the final velocities are v1 and v2. Let's try to find out what is v1, what is v2 in terms of u1 and u2. And we will take a very special case in which m2 is very less than m1. So, we are seeing the special case. Earlier, we have already seen a special case in which masses were equal. In that special case, the velocities get interchanged. And in this special case, we will see what happens. So, first equation, conservation of linear momentum. This equation goes like this. We have mass m1 times u1 plus mass m2 times u2. This is the initial momentum. This must be equal to the final momentum, which is equal to m1 v1 plus m2 v2. Now let's divide everything by m1. So when we divide everything by m1, we get this. Now you can see m1 cancels out. And m2 by m1. What is this ratio? m2 by m1. Yes. What about this ratio? m1 by m1 is actually 1. So let me just erase them. Okay. But what about m2 by m1? See, m2, we have taken it to be very less than m1. So this ratio is almost 0. So this is almost 0. So now we get the value u1 is approximately equal to v1. Approximately equal. Let me use a different sign. Okay. So you got the point. u1 is approximately equal to v1. Now, what was the second equation? The second equation was speed of approach is equals to speed of separation. Yes. So, the speed of approach in our case, speed of approach is nothing but u1 minus u2. This is the speed of approach. What is the speed of separation? Speed of separation is v2 minus v1. Okay. Now, let me just put the value of v1 as u1. So, what are we getting? We are getting u1 minus u2 is equal to v2 minus u1. Yes. And from this we are getting v2. v2 is coming out to be twice of u1 minus u2. Yes, this is what we get. And we have used these two equations to get the answer. And when we have used this equation, we got option A, 10 meter per second as the final velocity of the red smaller mass. So option A is the right answer for our question. A bus of mass capital M. Oh, bus is coming with initial velocity 15 meter per second. So a bus of mass capital M hits a man of mass small m standing on the road. I don't know why this man was standing in the road, but I think hospital guys will take a good care of him later on. Okay. If capital M is very, very large than small m, so mass of the bus is very, very large than small m, and initially the bus was moving with 15 meter per second, what will be the speed of man just after the collision? So just after the collision, with what velocity will this man fly? This is the question. And we have to assume that the collision is perfectly elastic. So there is no loss of kinetic energy and there is no loss of momentum. Energy is conserved and the momentum is conserved. So this is perfectly elastic collision. Now, I told you in the previous question, when we have a case where a very large mass collides with a very small mass, then in that case, we can memorize the formula of V1 and V2. What is the final velocity of the heavier mass? What is the final velocity of the heavier mass? Well, this velocity is approximately equal to the initial velocity of the heavier mass. Actually, the heavier mass does not go any appreciable change in velocity. Okay. And the velocity of the lighter mass, well, this is approximately equal to twice of u1 minus u2. And remember, caution, beep, 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 beep. Remember, u1 and u2 have to be taken with their respective signs. Yes? Okay. Now, let's use these formula and calculate the final velocities. So, what is V1? What do you think is V1? V1 is actually approximately equal to U1 and this comes out to be equal to 15 meter per second. Okay. And what is V2? Well, V2 we can see is actually twice of U1, twice of 15 minus U2. U2 is actually 0. So, we get the value of V2 as 30 meter per second. So what was asked in the question? The final velocity of the man. And we can see, let's draw a hospital for this man. So this man will fly straight into the hospital with a velocity of 30 meter per second. And option C is the right answer for our question. A ball of mass 1 kg is thrown with the velocity of 6 meter per second and it goes and collides with a stone of unknown mass which was initially at rest. So we don't know what is the mass of this stone, we don't know what is mb, but we know it was at rest. Okay. And if the velocity of the stone after the elastic collision with the ball is 1.5 meter per second, then what is the mass of the stone? So we have to find what is this mass of the stone if the final velocity of the stone after the collision is 1.5 meter per second. So these data are given. The mass of the golf ball was 1 kg and the mass of stone is unknown. The initial velocities were given and the final velocity of the stone is also given. Using that, we have to find what is the mass of the stone. Okay, so we got the problem. This was the initial situation before the collision and then after the collision, this is the situation. Fine. Now, how are we going to solve the equation? Well, let's write the equation first. So, let's write the equation for conservation of linear momentum. We can apply that equation because there is no net external force on this system. Okay. So initial momentum is equals to final momentum and initial momentum of the system is the momentum of the ball plus momentum of the stone. Momentum of the ball is mass of the ball times velocity of the ball which is 6 plus mass of the stone is unknown and the velocity of the stone is 0. So this is the initial momentum of the system. Okay? Yes. Now, final momentum of the system. For this, we write the momentum of ball plus momentum of the stone. Momentum of the ball is mass of the ball times the final velocity of the ball which is VA. And then we have momentum of the stone which is equal to mass of the stone unknown times 1.5, the final velocity of the stone. Agreed. So this is the first beautiful equation. 6 is equals to VA plus 1.5 m. Right? We will call it equation 1. Now let's write another equation. The other equation is when we have the elastic collision specifically. So, actually we can conserve the kinetic energy. The initial kinetic energy of the system is equals to final kinetic energy of the system. This happens only in elastic collision, perfectly elastic collision. The initial kinetic energy is equal to final kinetic energy. But that equation is too lengthy. So we will get a simpler equation. The simpler equation is like this. Speed of approach is equals to speed of separation. Speed of approach is equals to speed of separation. What is the speed of approach in the question? Can you see that the ball is approaching the stone? Yes, we can see. So what is the speed of approach? Speed of approach, very simple. It is 6. 6 minus 0 is the speed of approach, right? And what is the speed of separation? You will say speed of separation, this is 1.5 minus VA. Actually, finally, the stone is moving with 1.5 meter per second. It is moving with a higher velocity than the golf ball. So, 1.5 minus VA is the final speed of separation. Okay. Now, we have these two equations and we can see that when we add them, VA will get cancelled out. So let's quickly add them, and what do we get? We get 12 is equals to 1.5 plus 1.5 small m. Yes? Yes. Now, from this you can see 12 divided by 1.5. 12 divided by 1.5 is equals to 1 plus m, right? What is 1.5? 1.5 is 3 by 2. Okay. So we are getting 8 is equals to 1 plus m, and m becomes 7. So mass of the stone is 7 kg. Yes, 7 kg is the mass of the stone. And now let's go back and mark option C as the right answer for our question.